All righty, good morning, everyone. Welcome back to physics. Yesterday we had started this problem. So, again, just to remind ourselves that for straight wire in a uniform magnetic field, our force on the straight wire is given by IL cross B. And again, if it's not straight, in that case, our force on the wire is equal to the current integral of dl crossed by the magnetic field. We'll get there in just a minute. But in this case, we have a straight wire in uniform magnetic field. So what we're told is the magnetic field is pointing out of the board. We have this rectangular loop of wire, but we know on the bottom portion here, which has a length of 10 centimeters, there's a downward force of 3.48 times 10 to the minus 2, with a current of 0.245 amps running through it. And we want to determine what is the strength of this magnetic field. So we determined last time that, of course, the current has to be in this direction. The reason for that is, again, by the right-hand rule, start on with the fingers in the direction of the current, curl towards the direction of the magnetic field by putting our palm in the direction of the magnetic field, grabbing at the magnetic field, our thumb points downward. So that means it has to be to the right. And the last thing is we just want to determine the magnitude of this magnetic field. So again, we have a straight wire in a constant magnetic field, which means that the force on this guy is going to be IL cross B, or magnitude-wise, this is just going to be ILB times sine of the angle between the two. Okay. Now, again, just to remind ourselves, the angle here, specifically the angle between the magnetic field and the current. So in this case, my current points that way. My magnetic field points that way. So what's the angle between the two? 90, right? So in this case, my angle is simply equal to 90 degrees. And what's sine of 90? 1. So it's going to be the same thing as simply ILB. Right? So in this case, I have the magnetic force is just equal to ILB, which means B, the magnitude of the magnetic field, is just going to be that magnetic force magnitude divided by the current times the light. So pulling in my numbers, this is equal to 3.48 times 10 to the minus 2, divided then by the current, which is 0.2, what was that, 245 times 0.1. So this thing is going to have units of newtons per amp per meter. And we'll talk about that in just a second. So pulling in my numbers, what I find in this case is, according to that should be a B, not an F, should work out to be 1.42 Teslas. So this tells us that, one, the unit of a magnetic field is called a Tesla. So this is a capital T. One more capital T that we have to deal with. So again, we have period, we have tension, and now we have this guy, which is Teslas, right? Which is different. It's not a variable. This is a unit, which is the same thing as a Newton per amp per meter. So this is actually the definition. And we know an amp is a coulomb per second. So this is the same thing as a Newton second divided by a coulomb meter. So this is what we call a Tesla. So other units you'll find in this guy are what are called Gauss. That's the typical other one. These guys are related to each other. By 10 to the fourth, Gauss is the same thing as a Tesla. Okay, so, but again, that's just a different unit system, but SI units, we're going to use Teslas for our magnetic field. Not the car, but a magnetic field. Is doing okay? Not too bad. Nice and easy, right? So let's do another example. This one, we're going to have a non-constant or non-straight wire in this case. So let's look at this one. So this says I have a rigid wire carrying a current of I that is going clockwise around the loop, consisting of a semicircle of radius r and two straight wire portions. So I'll draw this in just a second. Then it says the wire lies in a plane perpendicular to uniform magnetic field of magnitude B0, that is into the board. So it's pointing into the board in this case. Says the straight wire sections each have a length of L within the field and wants to determine the net force on the wire due to this magnetic field. So let's draw our picture here, since we're not given a picture. So it says that we have two straight wire portions. So these are my straight wire portions. For each one of these guys is a length of L. So this is L. This is also L. And then connecting these guys is a semicircle. So this guy's doing this. You can draw that properly, which has a constant radius of r. Now, it also says we have a current flowing through this guy where our current is going in the clockwise direction, which means through here, I have a current going in this direction. this direction and this direction. So this is my current I. So it's going like this through the semicircle. And then finally, we have a magnetic field, which is pointing into the board everywhere along here. So this is my magnetic field. Wood pointing everywhere into the, and to draw like this. All right. So cool. So let's talk about this. So first things first, let's look at the straight wire portions. So in the straight wire portion, again, using our right-hand rule, we can determine the force on this guy and this guy. So again, we're going to point our fingers in the direction of the current, put our palm in the direction of the magnetic field, which is into the board, grab towards the magnetic field. Our thumb then points in the direction of the force, which means on this guy, our magnetic force will be to the left. Okay? Cool. For this one, our current now is going downward, so it's going down in this direction. Magnetic field, again, is into the board, so I put my palm in the direction of the magnetic field, grab towards the magnetic field, which means my force on this portion then is going to point to the right. Who's doing okay? Now, for this portion, again, we're going to do the same thing. So let me look at a little chunk here. So in this case, my instantaneous current points in this direction. So we're going to point our fingers in the direction of the current. Curl towards the external magnetic field. So again, my palm's going to point in the direction of the magnetic field, which it is. Grab, which means perpendicular to that is going to be my magnetic force here. So it's going to be my magnetic force from this small section. And then for this section over here, again, my instantaneous current is going to move in this direction, or at least the tangential portion. Again, point my fingers in the direction of the current, grab towards the magnetic field. My thumb then points off in this direction. So this is then going to be my magnetic force. Okay? Now, let's deal with the straight wire sections first. For the straight wire sections, these guys are straight wires in a constant magnetic field, which means they're going to satisfy this expression. Okay? Now, in this case, I know the lengths are the same. What's true about the current here and here? Also the same. And what's true about the magnetic field here and here? Also the same, which means what's true about the magnitude of these two forces? They're equal and they're in opposite directions, which means what happens to the total force? They're going to cancel, right? So in this case, this force here is going to cancel this force. So this means that what? If I was looking at the total force on this wire, my net force then, so my net magnetic force, would then be equal to the force from the left wire plus the force from the semicircle plus then the force from the right wire. Call that little r in this case. Now, what we just established was that the force on the left wire is the same as the force on the right wire, so those two portions are going to cancel. Okay. Now, that means the only force which is going to happen on this guy will then be from the semicircle itself. Okay? Now, what I also know is that this is a non-straight wire in an external magnetic field, which means that in this case, we're going to have to integrate. So this is going to be the current times the integral then of dl crossed by the magnetic field. And we'll talk about that in just a second. Now, the other thing is, I drew these two. These guys are symmetric, which means that what? If my force in this case is anywhere along here pointing perpendicular to the wire, what's going to happen then to the horizontal components of the force? They're all going to cancel, which means my total force is only going to point in which direction? Upward in this case, right? So in this case, my total magnetic field is only going to point in this direction. Okay? So it's my magnetic force. So F net then is going to point only in this particular direction. So what I need in this case then is something that's going to tell me it only points in this direction. So let's define this here as my angle of theta. So according to this magnetic force here, bless you, I only want the vertical portion, which means which trait term am I going to take? Sine, right? So let's call this then sine of the angle of theta. We're doing okay? Now, from here, what I know is this force is going to point in the vertical direction. And let me arbitrarily call that my y direction. So let's put in a coordinate system. So let's call that the y-axis. Let's call this the x-axis. So this says that magnitude-wise, this is going to be I, magnitude of the integral of dl cross b, sine of the angle theta, all in the j hat direction. We doing okay? Now, from here, we can now write the magnitude of this guy. So it's going to be the same thing as I. Magnitude of him is going to be the integral of dl magnitude, magnitude of the magnetic field, sine of the angle between those, which I'm going to call the angle phi, because it's not the same angle as this guy here, times sine of this angle theta, all in the j hat direction. Remember, this angle here is the angle specifically between B and I, where this is the angle relative to this guy, which tells me I only want the vertical portion. Is okay? So in this case, what we're defining is that this is my current, this is my magnetic field. We're calling this the angle of phi. So this is the angle between B and I in this case. Okay. So again, note we have two different angles in this case. We have the angle between B and I, and then we have the angle telling us relative to the x-axis, we only want the vertical portion. What's up? We'll talk about that. Let's talk about that. So good. So first things first is I want to talk about that angle phi. Good. So in this case, what I know is anywhere along here, my current then is going to point in the tangential directions. Right? So it doesn't matter where I'm looking at, it's going to be something like this. Right? Magnetic field is into the plane, which means that the current is doing anything in this plane where the magnetic field is pointing perpendicular to that plane. Which means anywhere along this semicircle, what's going to be true about the angle between the magnetic field and the currents? What's that? Stay the same, absolutely. And what is specifically that angle? So this is all happening in this plane. It's perpendicular, which means what's the angle? 90 degrees, right? So in this case, the angle of phi will always be equal to 90 degrees. Always. Because again, my current is moving in this plane, and the magnetic field is perpendicular to that plane, which means that angle simply has to be 90 degrees. Okay? Which means that this sine term is simply going to become 1. Absolutely. So in this case, this means that my magnetic field, the net magnetic field, will then be equal to the current times the integral of then dl crossed by the magnetic field. Actually, we'll do it this way. So it's going to be dl b sine of the angle of theta, all in the j hat direction. So like that. What's up, kidding? Yeah, anywhere I look along here, right? Because my current is moving only in this plane, and my magnetic field, we're told, is perpendicular to that plane. So anywhere along the current moving in this direction, it's going to be 90 degrees. In other cases, it may not be. Yeah.
Like in those cases, will there be
Yes. So you have in another angle, and we'll see that when we get to what's known as Biot-Savart's law. Yes. So we'll get there. We'll get there. Everybody's okay? Now, next thing is we're integrating over DL. So remember, DL, as I kind of drew it here, is the differential length, which is pointing instantaneously in the direction of the currents, right? Or over here, this is my DL. So my DL is the small section I'm cutting across this particular loop. Okay. Now, since this has a constant radius of r, how can I rewrite this differential length here in terms of the radius and this small angle here that this guy slices out? What am I going to use? Arc length, right? So in this case, my DL is going to be the same thing then as r d theta. Okay? Cool. So this is going to be the same thing as I times b, because b is a constant. I can pull it outside the integral, times r, which is also a constant, integral of sine of theta d theta, all in the j hat direction. Is doing okay? Now, in this case, we can integrate, because we're integrating along this direction here, we can either integrate from pi to 0 or from 0 to pi. Actually, doesn't matter because we already know the direction is the positive j direction, which means that we integrate from this side to this side. If we get a negative sign, we just have to make it positive because we already know the direction of the force is upward. If we use that negative sign, that flips the direction of the force, which means it would be feeling it downward, which we know is not true. Okay, so whichever way we want to do it, we just have to make sure we use the absolute value on this guy because we already know the direction is positive y direction. So which way you want to go, 0 to pi or pi to 0? 0 to pi sounds great. So let's do 0 to pi. 0. Great. So what's the integral of sine? Negative cosine. So it's going to be the same thing then as I times b times r times then the integral, which is minus cosine of theta evaluated from 0 to pi in the j hat direction. It's okay? What is cosine evaluated at pi? -1. So in this case, I'm going to get a -1 times a negative, which is a +1. So I'm going to get an I times b r times a negative of a -1 minus then a minus from here. What's cosine of 1? Or sorry, cosine of 0? 1. So I'm going to get a minus, and then I get this extra minus sign from here. So I make that a +1 in the j hat direction. What's minus minus 1 plus 1? 2. So at the end of the day, this guy's simply going to be 2 times I times b times r in the j hat direction. So this is my force. So the total net force on this guy only happens from the semicircle, where the magnitude of that force is going to be twice the current times the value of the external magnetic field times the radius of this particular circle. What's that?
So if, like, for example, the B angle wasn't perpendicular, so it wasn't 90, let's say, it was like 45 degrees.
Okay.
How would that change what we do there?
Oh, well, in that case, it'd be a little more complicated, slightly. So the angle between the two then would be, so if this was 45 degrees, then you would just have sine of 45.
Oh, and so that doesn't change it.
No, so that would give you a square root of 2 over 2. The only thing that would happen in this case now is the cross product becomes a little more complicated in the fact that your vector would point slightly in a different direction, if that kind of makes sense. Theoretically, yes, but in practicality, probably not. Okay, we'll make it as simple as possible. Yeah. And the other thing you can think of is I can always rotate my plane, right, to make it so that's always basically 90 degrees. I can always do that, right? So just rotate the plane that way. But yeah, I mean, if this thing was kind of bowed and then did weird things, it could be in the fact that part of it is 90 degrees, the other part of it is 0 degrees. So in that case, I would have to integrate technically over both angles. So that'd be a worst case type scenario. So in this case, if this started off in this plane, but then bent inward, so that it starts off here perpendicular, but then as it bends inward, it becomes parallel, say something like that. So in that case, I would actually have to integrate over both of those two angles. So, but then those two angles would be related to each other, so I'd only technically integrate over one, and etc. So, but yeah, but they'll be related to each other in that case. But we're not going to make it that complicated. It's going to be great. Everyone okay? Not too bad. So good. So next thing let's talk about is, let's think about the wire. So what we said is what? We have a wire here. So here's our wire in some sort of external magnetic field carrying a current. So again, this guy has a current. This guy is feeling an external magnetic field in this direction, and this guy's going to feel a force. Or again, we know the force on this guy, if it's a straight wire, is FB is equal to IL cross B. Now, what is current actually made out of? Moving charges, right? So let's think about what's actually happening on the inside. So what I have is actually a bunch of moving charges. Each one of these guys have a charge of 2. And we know that they're going to have a drift velocity, where that drift velocity is going to point in the same direction as the current, because we're pretending that these guys are always positive charges. Right? So what this means then is the reason that the wire is feeling a force is because of what? So what does this imply? So if a current is actually made of charges, and the wire is feeling a force because it has a current, what else is feeling a force? The charges themselves. So the reason this thing actually feels a force is not necessarily because the wire feels the force. It's because all of the individual charged particles on the inside are actually feeling a force. So the next thing we want to find out is how much force does each one of these individual charges feel by moving in an external magnetic field? This is what we want to look at, okay? Now, the way we can do that is we know these guys are going to feel what? A force because they're moving, which means I have my drift velocity in this direction. So what I can do then is I can say, well, this guy starts off here. It moves over some time frame of delta t, so it's going to move from this position here to, say, now this position here. So it's going to move some length of, say, L. Okay? Now, since it's moving with constant velocity, we can rewrite L then as simply the drift velocity times the change in time of delta t. Everybody's doing okay? So I can rewrite this then now as what? I times the drift velocity times the change in time crossed then by the external magnetic field. Now, again, we know the definition of current, though, is what? dq dt, or in this case, if it's constant, then we're going to have a change in charge over change in time. Okay, so it's going to be the same thing then as the change in charge divided by the change in time times my drift velocity times my change in time crossed by then the external magnetic field. Now, what's true about this change in time here and this change in time here? They're the same, so let's cancel that. So this guy's going to go away. Now, the other thing we know is that each one of these charges has the same charge, which means the change in charge then is simply going to be the total number of charges times the charge of that charge. Is okay with that? So in this case, I can finally rewrite this then as the force on a charged particle, or at least in this case, a collection of charged particles, will be the number of charged particles times the charge of the charged particle times the drift velocity, which I'm just going to call velocity, crossed then by the external magnetic field, or I'm going to isolate that n and write this as QV cross. So what this one says then is the total force acting on this wire is equal to the total number of charged particles I have times the charge of the charged particle times the velocity crossed by the external magnetic field. Which means for one single charged particle, the actual force is going to be QV cross B. Okay, so the total force in this case will just be QV cross B times the number of charges that I have. Okay with that? So what does this tell us? This tells us that the force on a single charged particle moving in an external magnetic field is simply given by F of B is equal to the charge of the charged particle times the velocity crossed by the external magnetic field. This then is the force on a single charged particle. Without getting the drift velocity, or it can be, in this case, if I'm looking at a single charged particle in space, that would just be the velocity at which it's moving. So initially it was the drift velocity because it was confined to moving in a wire. But now basically what I'm doing is I'm taking this idea and generalizing it to even a single charge moving in an external magnetic field. Okay. So you can think of that again as its drift velocity. Correct.
I personally thought you were going along with, you were saying that this is how current base magnetic force.
Right. Initially, that's where I started. So I started by saying so this guy feels the force because of the current, but it's actually because of the charges on the inside. And then this is what the force of a single charge would feel. Exactly. So in that case, this would be my drift velocity within inside of the wire. But now what I'm saying is I can also take that charged particle by itself, give it some initial velocity and throw it in an external magnetic field. And this is the amount of force it would feel.
And since the particles are already in the case that's wired, then the particles are
correct. Correct. Exactly.
But in this case, it's attractive. Like,
yeah, it would just be me taking a charged particle and kicking it across the room, right? So in that case, that would just be the velocity from that. Well, no, it'd be so what would create the current initially is the electric field. So the electric field creates the current, and then the current would feel a force due to the magnetic field.
Yeah. Sorry. Yeah.
You're fine. Is that okay? So that's it. So let's take this and let's start doing some examples with this. So this one says that we have an electron, which is moving at 2 times 10 to the 7th meters per second, which is relatively quick. A little faster than I could run, but not by much, right? In a plane, which is perpendicular to a uniform magnetic field of 0.01 Teslas. So that's the magnitude of the magnetic field. And it wants us to describe the path of the electron and go from there. So let's look at this guy. Let's talk about this guy. And let me write that equation back up here. So F of B is equal to QV cross B. Right? So what this is saying is I have an electron. Here's my electron. Okay. And it's going to be moving in some direction. So let's say initially it's moving in this direction with some velocity V, where we know the velocity V is that guy. Now we know it's moving in an external magnetic field, which is perpendicular to the velocity, which means it's either into the board or out of the board. All right. Andre, which way you wanted to go? Into the board or out of the board? Out of the board. Sounds fantastic. So let's take this guy out of the board. Oh, out. So this is my magnetic field. So let's think about what this thing is going to do. So this guy is moving this way. Magnetic field is out of the board. What's going to be the direction that this guy feels its force? So again, right-hand rule says we're going to put our fingers in the direction of the first, curl towards the second, and our thumb's going to give us the direction of the force. Okay? So in this case, I should draw this down a little further, but that's okay. We'll go with this. We're going to point our fingers in the direction of the velocity, this way. Magnetic field is out of the board, so we have to put our palm in the direction of the magnetic field. Curl, our direction of our force would be downward. Now, we got to wait 1 second. This is an electron. What's the sign of the charge on the electron? Negative, which means we have to multiply this thing by an extra negative at the end of the day. If I multiply by a vector by a negative sign, what does that do to the vector? Rotates in the opposite direction. So this guy is actually going to feel a force in this direction. Okay? Well, let me redraw down here so we can see it a little bit better, what it's actually going to do. So again, here's my electron. Again, I'm just redrawing this guy. So this is my velocity. Magnetic field is out of the board. So this is my D. So again, this guy's going to feel a force in this direction. So this is a good thing to note, again, when it comes to right-hand rule number 2. We're going to add an extra step on here. So step number 4 is going to be if we have a negative charge. In that case, we have to rotate by an extra 180 degrees. Okay. Or if you want to get all kinds of excited about it, you use your left hand. Instead of using the right-hand rule, use the left-hand rule. So for example, in that case, I put my fingers in the direction of the velocity, curl towards the external magnetic field, and my thumb now points in the direction of the force. As opposed to doing this and this, where it points in the opposite direction. So if it's a negative charge, you can use the left-hand rule. If it's a positive charge, you can use the right-hand rule. Or you can just use the right-hand rule all the time and then extra rotate by 180 degrees so you don't get all kinds of confused. Whichever works for you. Doesn't matter. I am more than happy with each one. And we're okay. So what have we established? We established this guy then is going to feel a force in this direction, which means what is my charge particle going to do? It's going to curve up in this direction, right? So this guy's trajectory then is going to be, this guy's going to start to move like this, right? Now let's consider a point here. So now let's say my charge particle is sitting here, which means its instantaneous velocity now points in this direction, right? So what's going to be the direction of the force now? So again, we're going to point our fingers in the direction of the velocity. Curl towards the external magnetic field. So I'm going to rotate my palm outward. Hope I don't pop my shoulder. Curl towards that. My thumb then is going to point in the direction of the force. But again, it's a negative, which means it's now going to go this way. Right? So this guy now is going to point in this direction at this point. Okay? Which means what's going to happen to this charge particle now? It's going to keep curving right? So now it's going to move to this location here. So now at this point here, my instantaneous velocity now is going to point this way, right? Tangential to the circle. Doing the same thing, velocity is this way, external magnetic field is out of the board, so I got to rotate this way, curl points in that direction, but again, it's a negative charge, so I got to do an extra rotation. This guy now is going to point in this direction. That was okay? Kind of see the pattern? What is this thing going to do? It's going to move in a circle. Exactly. It's going to orbit, right? So this thing ultimately is going to move like this, right? It's going to move in a circle. So our describe of our path in this case is that what? The electron will move in a circle of constant radius. Now, how do I know it has constant radius? Well, how do I know this circle here is going to have a constant radius? Let me call that R. Oh, shit. Go ahead, Gabby. Magnetic field's constant. Well, let's think about it too. How is the force relative to the velocity? It's perpendicular, which means what's the direction of the acceleration? Perpendicular, which means this thing's going to feel an acceleration always towards the center, which means its magnitude of its speed cannot change, which means whatever velocity I had here is the same thing as the velocity, or technically the speed here is the same as the speed here, which is the same as the speed here, which means what kind of acceleration is this? Centripetal, which means this thing is going to undergo uniform circular motion, right? So ultimately, this thing then undergoes uniform circular motion. All those beautiful things from 205 are coming back to haunt us. So great. So now we want to describe this path. We want to know, given the fact that we know the velocity, we know the external magnetic field, we know the charge, we also know the mass. What then is the radius, right? Because we know it's going to undergo a circle. So what's the radius of this guy? Now, the way we're going to do that is we're going to say that the sum of the forces acting on this guy then must be equal to mass times the centripetal acceleration. And remember what the centripetal acceleration is? V squared over R. So it's going to be the same thing then as m times v squared over the radius. Now, in this case, the only thing causing it to move in a circle, as we have drawn here, is the magnetic force. So it's going to be the same thing then as our magnetic force. So this is going to be what? Our QVB, sine of the angle between the two. Are we doing okay? Now we know in this case, though, the velocity will always be in this plane, and the magnetic field is which way? Perpendicular to that plane, which means what has to be that angle between the two? 90 degrees. Perfect. So in this case, this guy is going to be 90 degrees. And again, what's sine of 90? 1. So finally, I'm going to get a QVB is then equal to mv squared over. Now, the velocity on the left is the same thing as the velocity on the right. So this guy's going to cancel this guy. So finally, we're going to get a QB is equal to an mv over r. Or finally, we get that r is going to be the same thing as QB, or sorry, mv over QB. So this then is going to be the radius of the circle. Everybody's doing okay? From there, we now just want to plug our numbers. So we know this is an electron. So we know the mass of the electron is what? 9.11 times 10 to the minus 31. The velocity in this case, we know is 2 times 10 to the 7th. We know the charge is the fundamental charge. So that's 1.602 times 10 to the minus 19. And we know the magnetic field is 0.01. So plug in my numbers. What I find in this case then is this works out to be 1.1 centimeters. So this guy's going to undergo uniform circular motion with a fixed radius of 1.1 centimeters at this velocity. It was okay? What's up?
Please satisfy the first measure.
Yes, in a way, and we'll get there. We'll get there. So that'll be more appropriate for a closed loop, which will be a magnetic moment. But we'll get there. What's up?
obviously, protons can, they're different, but wouldn't it rotate in the opposite direction?
Correct. So if this guy was a proton, absolutely, then this guy would actually also create a circle, but it would rotate in this direction. So this guy was a positive charge, it would rotate this way, but the negative charge rotates in this direction. Absolutely.
So it's bigger though, because much more massive.
Correct. Absolutely. Because this guy has a much bigger mass to it, which means that's what? It wants to keep going in a straight line. Because it has more mass, that means the inertia is bigger, which means the centripetal acceleration will become less, which means it would feel less of an acceleration towards the middle. So yeah, so if this was a proton, for example, this circle would be more like that, right? The radius would be much bigger because it would feel less of an acceleration towards the middle, right? Because again, more mass means smaller acceleration for a fixed amount of force. Right? Now, other things to point out about this are, if this thing is going through a circle, that means it also has a period. So what do we know? We know that 2 pi times the radius must then be equal to the mass. Let's do it this way. The velocity times the period. So that is the amount of time it takes to go through a full circle. So let's solve this for the period. So our period then is going to be the same thing then as 2 pi times the radius divided by the velocity. Or since this guy has a velocity, let's solve it for the velocity. So it's going to be 2 pi times the radius divided by the period. So let's replace this guy here with then what? 2 pi times the radius divided by the period. So this means that QB is going to be equal then to M times 2 pi R divided by R times the period. What happens to those R's? They're going to cancel. So this R is going to cancel with IR, which means this is going to be the same thing then as 2 pi times the mass divided by the period. Or solving for the period, let's do that over here. My period then is going to be the same thing then as what? So 2 pi M divided by QB. So this then is the period. This is how much time it's going to take this guy to go through a full circle, which means it also has a frequency. How does the frequency relate to the period? 1 over, so finally our frequency is going to be the same thing then as QB over 2 pi M. Point something down. What's up? Any charged particle. Yes. Any charged particle. This has a special name. This is what's known as the cyclotron frequency. So the cyclotron frequency relates to the radiation that you would actually get off by accelerating a charged particle through a circle. So old particle colliders were actually created this way. So what happened in this case then is you took a magnet. So here was your magnet. And then you took a charged particle on the inside and you caused it to move around in a circle. Because it's accelerating, it actually radiates energy away. So what they would do in that case then is the energy which is being radiated, then they would either collect it or put it at some sort of target over here. And then it would use that radiation coming off to build a particle collider. This is the way that particle colliders were initially created, was by putting this guy into a magnet, causing it to move in a circle, and then collecting or directing all of that towards a target. Okay. Now, things to point out before I move on to something else is that number one, the magnetic force, again, is going to be QV cross B. Now, will the acceleration ever be in the same direction as the velocity? So meaning, again, if my sum of my forces is equal to m times a, can the acceleration ever be in the same direction as the velocity? No, it's always going to be perpendicular. So our acceleration will always be perpendicular to the velocity, which means what? It means that just like here, the magnetic field then can never cause its speed to change, is what this tells us, right? So what this means then is that the magnetic force can never cause the speed to change. I mean, obviously it can cause the velocity of the change because the velocity has to do with the direction, hence the centripetal acceleration. But that means it can never cause it to speed up or slow down. All it can do is cause it to move in a circle. Okay. Now, if all it can do is cause it to move in a circle, does that mean that, well, let me ask it this way. Can a magnetic force do work on a charged particle? No. Okay, because we know work is the force dotted by the displacement, which means the only way to do work is if the displacement is in the same direction as the force, but our force is always perpendicular to the displacement, which means that's what an initial caveat of this is that the work is always going to be equal to zero, which means that the magnetic force, i.e. the magnetic field, can never do work on a charged particle. Everybody's okay? Now, what does this mean? This means that what? Let's say that my charged particle comes in at an angle relative to the magnetic field. So let's talk about what happened in that case. So let's say my magnetic field points in this direction. And let's say the velocity of my charged particle, bless you, comes in at some angle v relative to the magnetic field. What would happen in this case? So in this case, these two are not perpendicular anymore. It's coming in at some angle relative to the magnetic field. What is this guy going to do? Good. It's going to create a circle based off of the perpendicular component of the velocity. So this is going to cause it to move in a circle. What's the parallel portion going to do? It's going to make it spiral. So ultimately what this thing is going to do is this charged particle is actually going to spiral in this direction. Okay. Where it's going to move along the direction of the magnetic field because the parallel portion is not going to feel a force, but the perpendicular portion is going to cause it to spiral. Okay. This distance from here to here is going to be fixed. So all these distances here will be equal to each other. This is what's known as the pitch. So the pitch then is the distance it travels during this time, where my pitch then is just going to be equal to the drift velocity times the time it takes to create a full circle in this case. So this is what we call the pitch. So the pitch is basically how far does it travel in the time of a period, basically. So technically, if you want to be more technical about that, this should be actually the period. So that's what we call the pitch. Now, a beautiful example of this is, let me bring this up on my laptop here, or my laptop, my iPad. So let's go to our figures here, CM4. It's actually this. What is that? The Northern Lights or the Aurora Borealis, right? This is actually what it's created from. So what happens is, so let's talk about this guy. The sun over here, as we talked about before, creates solar winds, which then interfere with the Earth. So here's my Earth. Now, effectively, what the Earth is basically a bar magnet, which means our magnetic field is going to do something like this. Is okay? So what happens in this case is we're going to get solar winds, which are going to come in. So let's say this solar wind is traveling. Let me say it's traveling in this direction for funsies. It's going to get caught up in the Earth's magnetic field, which means it's going to start to spiral along the direction of the Earth's magnetic field. Okay? As this guy is spiraling in, what happens to the strength of the magnetic field closer to the Earth itself? It's going to increase, right? Because I have a bigger density, which means as it increases, what happens to the radius? Gets smaller, right? Which means as this thing is in spiraling, the radius is going to get smaller and smaller and smaller, right? As the magnetic field increases, though, what happens to the frequency? Increases, bless you, which means that going back to here, the amount of radiation that it gives off will get bigger and bigger and bigger and bigger. Okay, which means as the radiation gets big enough, what will happen then is they will start to ionize the air around it, which means that it's actually going to strip electrons off of the oxygen to ionize the oxygen. That gives off light. What is the color of the light? Give you an hint. Green, right? Now, as that charged particle passes, it will then not ionize, it'll recombine, so that electron will go back to the hydrogen atom, which also gives off light. And what's the color of that light? Green, because it's the same energy levels, right? Which means that what you're actually seeing here are the directions of the Earth's magnetic field. So the aurora borealis here is actually the direction of the Earth's magnetic field. And all you're seeing is the charged particles wrapping around that, ionizing the light, which then is creating this beautiful green color. What's up?
Like as opposed to sort of weighted.
Oh, well, technically, right. So because the Earth's magnetic field would be the lines here, I mean, but you would have other lines that basically stretch in here. It's just how many how many charges get caught up in that particular magnetic field line.
So like,
So, correct. So the more you would see that, exactly.
which is why there's like, which is why everything is. That's
Correct. Yes.
Because I was like, I know there's lines, but they're infinitely many lines.
Correct. But yeah, it has to do with the number of charged particles which you get caught up in a particular line. Absolutely. What's up, Dana?
Oh, it's the end. Is there waiting for you?
It's not a goal. I don't know. We'll have to find out. With little leprechauns there too. So what's up, Homer? The color can be different. I mean, there are mixtures of colors in there. So the primary is green because most of our atmosphere is oxygen, but it's also going to ionize the nitrogen and whatever else is in there as well. So technically inside of here, you will get secondary colors from basically ionizing the nitrogen and everything as well. But the predominant number is the greatest amount of concentration is the oxygen, which is why you mostly see the green. But yeah, but there are other things in there as well, but they're subdominant in the fact that they're not as bright because there's less number of ionizations of things like nitrogen. But yeah, technically it's a mixture of different colors in there. So what's up here?
So what affects its span? Like how far it reaches? Is it like the speed that it hits or the size of it?
You mean how far it comes down?
Yes.
Um,
Is there a speed where it can be seen in like northern parts of the US?
right. So that has to do with more of the incoming velocity at which it has. That's right. So if it comes in with a much higher velocity, then the radius in here would be increased, right? And then as the radius is being increased, then that technically would then increase also the velocity that it, or the frequency it has in this case. So yeah, so the more incoming velocity it has, then you would see it basically starting at a lower level, as you said. So northern states, for example, would see it instead of just Alaska or the North Pole or things like that. What's that getting?
You sort of answered my question because I was
Right.
going to ask it. I was just sort of asking about how we can see it.
Yeah, so that would be more high energy photons and, or not photons, sorry, charged particles like protons and photons. Exactly. Oh, so that has to do with how big those promenades are. So as we talked about before, we get the magnetic field, which then bursts through the surface of this guy. So that drags charged particles with us. So the bigger this guy becomes and then explodes, that will give off larger velocities of the original charged particles. Okay. Not to mention, we can have cosmic rays coming from distant galaxies. That's also true. So in that case, we can also get those guys wrapped up as well. But again, you would have to have a high concentration of those guys actually moving in. So, but yeah, but typically the more the velocity is, has to do with the higher the flare basically given, which is when the promenade breaks. So the smaller promenade, then the smaller the solar flare, so the smaller the velocity would be. That's a good question. I mean, I would imagine, yeah, if you could take a high enough concentration of charged particles at a big enough energy and then wrap it around the magnetic field. So you could probably do that inside of a particle collider, but you would have to be able to see inside of the particle collider. And usually that's shielded, so you don't lose that radiation. So, but yeah, I'd imagine you could be able to do that in something like a particle collider. Because there you're talking about velocities of particles, which are like 99.99999% of the speed of light. So those are ridiculously high energies. Yeah. So yeah, inside of there, you also have magnets where the magnet helps to steer the charged particle. So yeah. So I'd imagine what would happen inside of there. So, are we looking at it? So next time we'll talk about some other stuff we can apply this to, like the discovery of the electron, where that actually comes from mass specs for my chemistry class over here. We'll talk about that guy as well. So yeah, we'll put more applications of this guy. But in the meantime, have fun. I'll see you guys tomorrow. Auf Wiedersehen. Auf Wiedersehen. Tschüss. Ciao. Bye-bye?
Yes.
No. At least not in my research or anything. So.